today we're going to talk a little bit about caffeine. Now you probably know that caffeine is found in soft drinks and coffee and even chocolate. Today we're going to look at what happens to the amount of caffeine in your body over time. So I'm not sure in your science classes if you've talked about half-life yet or not. Half-life is the amount of time that it takes for half of a substance in your body to go away. So if I start with 100 and the half-life is 2 hours, after 2 hours I would have 50 milligrams of caffeine left, okay? So for our experiment today, we're going to start with 64 milligrams of caffeine, and every square on my paper here represents 1 milligram, so I've got 64 squares. And the half-life of caffeine is about 5 hours, so we're going to use that for our experiment today. So let's say I drink something that's got 64 milligrams of caffeine. After 5 hours, half of that's going to go away. So I'm going to mark out half of my boxes up here. Okay. So after that 5 hours, this half is gone. That means I've got this number of milligrams left, which is 32, because that's half of 64. Okay. So now, after 5 more hours, another half is going to go away. So half of 32 is 16. So I've got 16 milligrams left after 10 hours. 5 more hours pass, you get to 15 hours, another half goes away. So I'm going to mark out half of that. Half of 16 is going to leave me with 8. Next step, same thing. Half of 8 means I'm only left with 4. Same thing for the next step. Half of 4, I'm going to mark out 2. Means I've still got 2 left. Mark out half again. So that means I've only got 1 left after 30 hours. Another step. Now I've got 1 whole block here. If I mark out half of it, that means I'm left with half of a milligram. Now I've got half a block. So if I mark out half of that, that means I've got 1/4 of a milligram. And we could keep going, getting smaller and smaller and smaller. Okay? So let's graph our data and see what it looks like. Okay, so let's go to Desmos.com and see what our graph looks like. So I'm going to click Start Graphing. Okay, so to add a table, you click the plus sign in the top left corner, go down to Table, and I'm going to put my X values in. And then I'm going to go up and put my Y values in the same way. And it should automatically graph our points. Zoom out just a little bit so we can see them. There we go. So you can see at 0, when we first drank the drink, it was 64 milligrams of caffeine. And then after 5 hours, we were down to 32, then 16, and so on. Notice that this is not a straight line. It's not a linear function. This is an exponential function. So it's decreasing at an exponential rate instead of like a linear function decreasing at where you add or subtract a number every time. Exponential functions happen when you multiply or divide some number every time. In this case, we were dividing our numbers by 2 every time because we were halving. We were doing the half-life. So I think we mentioned it earlier. These numbers would get closer and closer to 0, but they would never actually reach that 0 line. So let's look at the exponential decay formula, which will be a little bit quicker. We won't have to graph every time. Let's look at it on the next slide. Let's look at our exponential decay formula. And it says f of x is a times b to the x power. A is your initial amount. That's your starting point, the point when x equals 0. Your b stands for your rate of decrease. And to get that, you say 1 for 100% minus your percent of decrease as a decimal. So if it's 25%, you have to change it to 0.25. If it's 55%, it would be 0.55. And then x is the number of time periods that have passed. So let's use this formula for our next example. Let's look at another caffeine example. So a Hershey bar has 9 milligrams of caffeine. And let's use our exponential decay formula to complete the table. So once again, our half-life is 5, so I'm going to go ahead and fill in our hours by 5s. And we are starting with 9 milligrams of caffeine. So our formula said y equals AB to the x power. In this case, A, our initial amount, is going to be 9. B, to get our rate, we're going to do 1 minus, and since it's half-life again, half as a percent is 50%, which as a decimal would be 0.5. And then x is our exponent. So if we simplify our formula just a little bit, 1 minus 0.5 is 0.5. So there's the formula that we're going to use to calculate the caffeine. Now if you'll remember on the last slide, we talked about the x is the number of time periods that have passed. So when you're dealing with half-life, the number of hours of half-life is 1 time period. So after 5 hours, that's 1 time period that has passed. After 10 hours, that's 2 time periods that have passed. So for our exponent in our equation, we're going to use this middle column, and that's got our hours converted to time periods. Okay, so if I start with the first one, I'm going to do y equals 9 times 0.5 to the first power. And if you work that out, I'm going to use my calculator to help me out just a little bit. You end up with 4.5, which makes sense because 4.5 is half of 9. So if you go to the next step, we're going to do the same thing except our exponent is 2 this time. So if you use your calculator for that, you get 2.25. All right, the next one, our exponent's going to be 3 this time. That's 3 time periods, or 15 hours have passed. And we're going to get 1.125. So you can already tell, just like the other one, we are decreasing, but it's not at a constant addition or subtraction rate. Okay, since we're dividing by 2 or multiplying by half, it's going to be another exponential graph. If we were to graph this, it would be a curve, just like the last one. So I'm going to go ahead and fill in these numbers just so you can see what happens every time. They are getting smaller. So we would be approaching 0 again. So even after 35 hours, that's more than a whole day, you still have caffeine in your system from eating that 1 bar of chocolate. Okay, so let's look at some more examples to go with exponential decay. So there's our formula again at the top. They use some different letters, but they mean the same thing. C is our initial value, the starting number that it gives us. R is our decay rate, and don't forget to change your percent to a decimal. And T is the number of time periods, again, just like the X in our equation. So let's start with number 1. It says a $24,000 car depreciates at a rate of 10% per year. And they want us to tell C, and they want us to tell R, and then write the equation for the problem. So C is our initial value. So our car costs $24,000 to begin with. And our rate is our percent as a decimal. And to change a percent to a decimal, you move your decimal 2 places to the left. So our rate is 0.10. So if we set up our formula, it's going to look like 24,000 times 1 minus 0.10 to the t power. I'm going to use t because that's what the directions said to do. And then if we clean it up just a little bit, 1 minus 0.10 gives us 0.9. And that would be our equation for that scenario. Okay, number 2, it says a stock is valued at $300. Then the value decreases by 9% per year. So once again, our C value is our initial value, so that's going to be that 300. Our rate, 9%, if you convert that to a decimal, is 0.09. So if we write our equation for this, it's going to be y equals 300 times 1 minus 0.09 to the t power. And then we can clean it up just a little bit. 1 minus 0.09, is 0.91 to the t power. And number 3, you buy a used car for $9,000. The car depreciates at a rate of 9% per year. Find the value of the car after 10 years. So our car started at $9,000. Our rate is 9%, which will be 0.09 as a decimal. And it says our time period is 10 years. So if we plug this in our formula, 9,000 is the initial value, 1 minus 0.09, and 10 is going to be our exponent. One minus 0.09 is 0.91. So I'm going to plug this in real quick. and I get 350.47. And I'm going to leave that at 2 decimal places since we're talking about money. Alright, I hope you learned a lot about exponential decay and the formula for that. And if you want to practice this some more, it's on page 21 of your Algebra 1 packet.